All right. Well, hi everyone. Thanks for coming back for the coffee break to listen to the second part of this tutorial. Uh, let's go ahead and begin. So my name is William K. Moses Jr. or Billy. And in the first part of the tutorial, Anisur talked about dispersion, explained what the problem is, motivated it, and talked about some of the papers that solve this problem, the vanilla setting. And when I say vanilla setting, what I mean is either synchronous or asynchronous communication. Time is either synchronous or asynchronous. Communication is local. And the question is, how do you balance time with the memory used by the robots? Now, that was a line of work that a lot of people pursued for quite some time. I'm here to talk about other lines of work people have pursued. And in this talk, what I want to do is I want to give you a taste of these extensions. And what I mean by that is this. I do not want to explain every detail of every technique used. I don't want to list out all the results, and I don't want this to be like something of a lit survey. My goal with this part of the talk is to give you a flavor of the techniques involved. So with that in mind, you can see if working with that particular type of extension seems interesting to you. And we'll be looking at 4 types of extensions that have been explored. I'll be explaining what the extension is, why you should even care about it. Once that's done, I'll talk a little bit about what work has already been done in that area. And then we'll deep dive with just one big technique or idea, and we'll go into it and see how this addresses the issues of that setting. And then, of course, we'll talk about some open problems. So let's get going. There are 4 types of extensions. The first is all the algorithms that Anisur talked about earlier, they were deterministic in nature. Now, some algorithms are actually randomized algorithms. Another extension is fault tolerance, where some of the robots can either be can either crash, or they can be Byzantine in nature. The third extension that Anisur mentioned a bit about is global communication, where instead of robots only being able to talk to each other when they're at the same node, regardless of where they are in a graph, they can talk to each other. And the final extension is when the graph has some form of dynamism, how do you still solve this problem? Now with that, let's get into these one by one. First of all, let's look at randomness. First of all, as I said, all the previous results, they were deterministic. Now, why is randomness even interesting? Well, this was already touched on in a question from the first part. How low can you go in terms of memory? And the thing is, when you have deterministic solutions, for a moment, if you have K robots, you need at least log K bits of memory to differentiate between 2 robots. And if you have N robots, that would be log N. But the thing is, you can use randomness to reduce this memory. Now, what's some of the work that's been done before? Well, there was a small paper in 2019 that actually just studied dispersion, the time to achieve dispersion on different types of graphs when you just use random walks. Another work was done by Anisur and myself in TAPC, where we use randomness. Instead of just talking about random walks, instead of using it to choose where we move, we use it to reduce the memory. We'll get into this in a bit, and we'll talk about how this was done. And the third type of memory, third result, is a paper by Das, Bose, and Sao that was in CalDAM, that actually improved on the 2019 TAMSI paper, in that we reduced the memory from log n to something lesser, and they reduced it even further to an optimal value of log delta. Now, let's deep dive into this particular paper, the 2019 TAMSI paper. So first of all, as I mentioned before, the purpose of using randomness for us was to reduce the amount of memory needed. And why? How? Well, if you have n robots, you need log n bits of memory to differentiate between them. And I should mention that, as Anissa mentioned in the first part, dispersion is typically talked about for k robots on n nodes, but the simplified version is just n robots and n nodes. And techniques I'll be talking about, I'll assume that we have n robots and n nodes. And the thing is, when you have n robots and n nodes, there's a lower bound that you need log n memory to differentiate between them. Each one needs a unique ID, so that you can so that if all the robots are together at a node, one of them needs to be able to settle down at that node. And this unique ID is used to actually differentiate between them and have one robot settle down. The way we use randomness in this paper is we use it to break symmetry. Essentially, when you have a bunch of robots at a given node, if you have all of them flip a coin such that those robots that land up heads can continue to participate, and those that land up as tails are not chosen, eventually, with high probability, exactly one robot will flip heads, and that robot can choose to stay at the node. And the thing is, you don't really need to, all you need to do is remember the result of the previous coin toss, and remember if you're allowed to participate or not in the next coin toss. So you just need, each robot just needs all 1 bits to make this happen. And a leader can be elected within a given round. Why is that? Because in this paper, what we did is we actually divided a round into a number of sub-rounds. And you might say, wait a second, is this even allowed? The thing is, yes, because in a given round, communication is considered as free. Local computation is considered as free. Really, a round is used to differentiate between movements of robots. Because typically it's considered that talking and locally computing something is very fast, but for a robot to actually move from one node to another, that takes quite a bit of time. So when robots are at the same node, if you were to break up a given round, which is some interval of time, into a smaller bunch of sub-rounds, you can use these sub-rounds to actually choose the leader. Now let's look at how this algorithm might actually work. You've already seen how dispersion algorithms work, so this should be fairly simple. The way things work is as follows. If, suppose for a moment you're in a cycle, and also assume that all the robots start at the same node, each one just needed all 1 bits of memory, and this leader election, this leader selection that I talked about earlier, it's run in 1 round. One of the robots will settle down, and the rest of them will just leave through the same port. Again, this process of leader election is repeated for 1 round, and one guy is selected, he settles down, the rest move. And this, after O of n rounds, every node in the ring will receive, will have a robot settled at it. And the thing is, for the ring, what you can do is the moment the robot settles down, it can choose to terminate. Because we know in a ring, no other robots won't have to come back to that node. And one very important thing to realize is this. Dispersion is all about having, if you have n robots, because it's a simplified setting, it's all about having 1 robot per node. And when you have the thing is this, if 2 robots are on the same node, they decide if one of them was settled down, in order for the other robot to know it was settled down, it needs to talk to that robot and say, hey, are you already settled down here? When that robot replies and says, yes, yes, I am, then this other robot can keep moving along. But the thing is, if a robot settles at a given node, but then terminates the algorithm, which is it does not participate in any future actions, subsequent robots, when they get to that node, they're unable to tell that a robot settled there. Because when they yell out into the void, hey, is anybody on this node with me? Nobody will reply. So this is why we have to be, so this is why it's very simple when it's a ring. But if it's not a ring, if it's a tree, we have to be a bit more careful because we have to be careful about when robots terminate. That's the difficulty here. The way we deal with this is we take up a 3-phase protocol. And now the point of the phases is as follows. In the first phase, you get the robots to settle down where they need to be. In the second phase, you have this one robot that was the final robot that would have settled down. You use him, you send him back to the root, back to the starting position. And in the third phase, you use this one robot to tell everybody else to turn off and terminate the algorithm. And finally, this one final robot, it'll go back to its empty position and it'll also terminate. So let's actually look at how it's done. So in the first phase, it's a simple DFS. So 11 were there, one guy settles, they move on, settles, so on, so forth. This is done until at the very end, there's only one robot left that's still moving around. Because remember, this is end robots and end nodes. So there's only one robot moving around. And he finally comes and he can settle down. Now, the moment this one robot finds an empty node, it realizes, oh, you know what? Phase 1 is over. Everybody else has settled down wherever they wanted to. Now it's time to start phase 2. Where phase 2 is, okay, I need this one robot, this guy who's on this blue node, this unoccupied node, to go back up to the starting position, the root of this tree. And importantly, as he goes back up, he tells each node, hey, this port leads to the final resting place of me. And when he goes here, he says, hey, this port actually leads to a final resting place. This port leads to a final resting place. Now, eventually, this robot will come back to the root. And now all it needs to do is it needs to tell people, okay, terminate. Now, it's a little interesting here because what's happening is for most of these nodes, a robot will terminate once the robot will tell this exploring robot will tell the settled robot, that is the robot who was already there from the first phase, hey, you're allowed to terminate the algorithm once this exploring robot, the one who's moving around, has explored all the ports from that node. So if we look, this robot has reached to this leaf node. Now, clearly it's explored the node when it's about to leave. So it'll tell this guy, you can shut off, and this exploring robot will go back to the parent. Now he'll continue exploring here, and he'll be able to tell these two guys to shut off. And once he comes back here, once all the children of this guy have been explored, he can tell him, okay, you can shut off. But now, the moment we get back to the root, both the root and every node along this path, from the root to the final resting place of this exploring robot, there's a slight tweak. The exploring robot only tells these nodes to shut down once it takes the port that leads to the final resting place. So for example, this exploring robot, it knows that once it leaves through this port, it's going towards the final resting place. So it tells the root, you can shut down now. This similarly for this node, once this exploring robot knows it's about to take this port that leads down. So it'll tell this node, the exploring robot will tell the settled robot, all right, you can terminate. Now here, First, the exploring robot has to explore some other edges. So it'll explore, tell this guy to shut down, tell him to shut down, explore somehow, tell him to shut down, come back. And now, when this exploring robot is about to take this path to the final resting place, it'll tell this robot, shut down. And now, once it's completed this and it's back to the empty node, this robot can say, I'm done with all of this, I'm shutting down. Okay, simple enough. We solved this termination issue, but we're not done. Because while this worked easily enough for a tree, for a graph, the problem is you have back edges. And the thing is, you don't want to tell a robot to prematurely terminate or shut down and then take a back edge to that robot later and think, oh, I reached an unexplored node. That's the danger. And so now the issue becomes for an arbitrary graph, although actually, sorry, I should say rooted graph because the robots are all at this node. The issue becomes identifying back edges. And so we have two solutions here. One is that the robots, each settled robot will maintain its distance from the root. So, I mean, when the moment a robot settles, it can actually remember how far away from the root it had to explore before it settled down, or at least the distance to the root of its parent, and it can recursively compute this. And the moment the exploring robot moves from something at some level I to some level j, which is smaller than I, it can determine, oh, you know what? We're out of luck. So for instance here, these exploring robots, the guy who settled down here has a distance to the root of 2. And the moment these exploring robots come here, the settled robot over there, its distance to the root is 0. So these exploring robots realize, oh, we hit a back edge. Let's go back. In this way, you can continue. Oops. And you'll end up with the one robot who comes back here, and then you just repeat the previous process. This is one such way. The other way this only requires the maximum of log delta, comma log d bits of memory per robot. Log d here is d is diameter. Another approach to remember these back edges is that simply each robot just maintains delta bits of memory, and it just 1 bit per edge. And the edges that are forward edges, it just stores those as 1. And the edges which are back edges, it stores those bits as 0. Simple enough. Now, in this manner, we can actually solve this problem using either the maximum of log d, log delta bits of memory, or in fact, just delta bits of memory. The thing is, this is an intermediary solution, and I mentioned earlier that there's already a paper that improves on this. What they did was, they realized the key insight here, that, what did I say? I said we needed this extra memory to determine back edges. But you really don't. In the process of the algorithm, recall that algorithm, if you're careful about keeping track about when robots should be shut down and when they should be awake, you don't actually need extra memory to remember what's a back edge and what's not. You can actually make the decision locally. And so you should check out that paper, the one I mentioned, that actually gives this log delta solution. Now, when it comes to open problems feature work, first of all, as you've probably seen from all the examples I just gave, we considered a gathered initial configuration. That is a rooted, every robot started the same node. We don't know how to do this when robots start at different nodes. I should say we don't know how to do this using O of log delta bits of memory. Can it be done? We don't know. Be something worthwhile. Another thing is, can these ideas be extended to the asynchronous setting? Now, when you look at the algorithm, one thing you should have noticed is Well, actually, I should preface this by saying, in the first part of the tutorial, where Anisar talked about a lot of the algorithms that work in the synchronous setting, when you go and look at those algorithms, you'll notice that a lot of those algorithms have require the robots to maintain a time counter. And typically, they know that each robot will, based on the algorithm, the robot will know that the algorithm terminates in some X number of rounds, where X is typically some O of N. And the idea is, if you can just maintain a bit counter, so some log n bits, you can actually count until time is done and then stop. And this is very useful when robots are far away from each other. If you notice the kind of solution we proposed earlier, we didn't do that. There was no round counter. It was one guy who went first, everybody settled down, and then this guy went and said, okay, you shut down, shut down, shut down, shut down, shut down, shut down. So it's more an event-driven approach. So you might say, oh, doesn't this immediately work in the asynchronous setting? And the answer is no. Why? Because of the leader election part of it. Recall that in order to actually elect the robot to settle down each node, we had divided each round into sub-rounds. So we were intrinsically making use of time. So this is something else that would be interesting to see. Now, the next thing I'd like to talk about is fault tolerance. So first of all, fault tolerance means what? It can mean either crash faults, where a robot, it was just performing its function and then it suddenly shut down. That's it. Or Byzantine faults, where the robot doesn't shut down. The robot instead can act in unexpected ways. And typically the way we model this is we assume that there's some omniscient adversary who controls all of the so-called Byzantine robots and can coordinate them to work in the worst way possible to defeat the algorithm. Because I mean, if you're dealing with unexpected faults, why not deal with the worst case situation? And why would we even consider this? I mean, the motivation is kind of simple, because in the real world, failure is the norm, it's not the exception. That's more common to deal with these kind of faults. So let's look at what's been done. So initially, Molla, Mondal, and myself, we introduced this problem of Byzantine dispersion, and we studied this on rings. I'll get to it in a moment, why we call it Byzantine dispersion, why we had to redefine the problem in the context of Byzantine robots. But anyhow, this paper, in 2020, we introduced the problem Byzantine dispersion, and we studied in a ring. Subsequently, we were able to expand our work to arbitrary graphs, where we studied both weak and strong Byzantine fault tolerance. Weak and strong, I'll get to that when I get to the model. And also, there has been work done on fault tolerances, crash faults as well. Patnaik, Sharma, and Mondal in ICDC and adjunctive proceedings, they studied effective crash faults on dispersion. So here, what I want to do is I want to deep dive into this Byzantine dispersion on graphs, where I can both explain the problem Byzantine dispersion and explain the issues when you deal with Byzantine robots, and explain the kind of high-level technique that we typically use to solve this problem. So, first of all, why do we need to redefine this problem statement? Well, the thing is, Byzantine robots can do what they want. So the original definition of dispersion, once again, assuming n robots on an n node graph, if you want one robot per node, but Byzantine robots, they don't care what you want. They could just permanently settle down at some other robot or settle together at some robot, and you can never solve the problem. So it doesn't make sense to solve the original problem when Byzantine robots are present. So instead, what we do is we solve this slight variant, Byzantine dispersion, where if you know that at most f of the robots will be Byzantine, then for the remaining non-Byzantine robots, what you want is you want these robots to settle down at nodes such that at most one good robot, that is non-Byzantine robot, is at each of these nodes. In other words, take care of the good guys, ignore the bad guys. Here in this final solution, you can see that there's a node here that has one good guy, one bad guy. We don't care. It's a valid solution. Once again, we can't control the bad guys. So with this problem statement in mind, let's go into the model a bit more. Once again, n-node anonymous graph with port labels. Here I've taken the port labels to be from 0 to small delta. So 0, 1, 2, 0, 1, 0. There are n robots, at most f of which are Byzantine. And once again, so these circles are the robots. Each of them has a unique ID. For ease, I've just written 1 to 8. So the IDs, they can be anything. And they're initially arbitrarily placed. Time moves in synchronous rounds, such that in each round, you have local computation and communication, and then subsequently movement, if any. So here the robots might talk to each other, then they might decide where they might move, and then they'll make. Finally, recall earlier I said that you have results for both strong and weak Byzantine fault tolerance. What is this notion of weakness and strongness? Well, Byzantine robots are robots that can lie. They can lie when they communicate with other robots at the same node. They can send incorrect information. They can also Shreyas, did you turn the video off by chance?
Yes, so your voice is cracking, so I thought it would save bandwidth.
Oh, I see. Let me also turn off my video in case that helps. Does this help?
Yes.
All right, great. Okay, in that case, I'm unable to see if anyone has questions.
Yeah, I can.
So I should have mentioned this earlier. Okay, in case anyone has questions, feel free to interrupt me at any time in this talk. So coming back to this, Byzantine robots, what can they do? Well, when two robots are located in the same node, this Byzantine guy can lie to the other guy. He can say whatever it wants. It can also move wherever it wants. If the algorithm had dictated that this robot 4 should have moved to this node, 4 can do what it wants. It can stay here, it can move elsewhere. However, the single discriminating factor between so-called normal Byzantine robots, otherwise known as strong Byzantine robots, and the weaker variant is that for weak Byzantine robots, when they send a message to some other robot co-located with them, they cannot fake their ID. In other words, whenever a robot sends a message to somebody else, it's sending that message and its ID is attached to it. If it's a weak Byzantine robot, it cannot change the ID. While it can change anything in the rest of the contents of the message, it can't change the ID. Strong Byzantine robots can change the ID. That's it. That's it for as far as the model is concerned. Now, one second. Let me just check one thing. Okay. Now, in this setting, we have 3 performance measures. One is time, the number of rounds until all non-Byzantine robots terminate. The second metric is the fault tolerance of the algorithms. For a given algorithm, how many bad guys can it tolerate? And the final metric is the strength of the fault tolerance. For a given algorithm, can it tolerate only weak Byzantine guys, bad adversary, or can it tolerate strong Byzantine robots? So with this in mind, in the paper that this comes from, almost every technique consists, almost every algorithm has 3 parts. The first part is gathering the robots. The second part is creating a map. In other words, an isomorphic copy of the graph. And the third part consists of the actual dispersion. That is, once the robots have created a map, they decide where to settle down. Now, I won't go into gathering because gathering can be from other papers. We use other solutions. But I will talk about the creation of the map and deciding where to settle down. As I mentioned, there are three metrics involved. One is the running time, the other is the Byzantine tolerance, and the final is what type of fault tolerance. So here, in order to illustrate the techniques, I'm going to talk about algorithms that take n power 4 and n cubed time. They handle up to n by 2 robots or n by 3 robots. And they only handle weak Byzantine robots. So with that said, let's look at these two steps. First, let's look at how robots can create a map of the graph. In other words, how they can learn about the entire graph. Now, let's look at this in a setting where there are no Byzantine robots. Let's pretend we just have two robots. Let's say here, robot 1 and 2, and they have to discover this graph. Now, there's a simple solution, the Explorer token problem. Explorer token technique. It's from the Dune, Pelk, and Pellick, 2014. It takes only n cubed rounds, and the way it works is one robot acts as an explorer, the other acts as a token, and they learn the graph in increasingly larger balls. For instance, here, both these robots, they only know about the starting node that they started at. First, they'll learn about all robots that are distance 1 away from it, from the starting node. Then they'll learn about nodes that are distance 2 away, then 3, and then 4. Now, let's actually look at the technique itself. So again, there are two robots. These are non-Byzantine, that is, they're good guys. And let's pretend that they've learned the graph up to some distance r. So as you can see here, almost the entire graph has been discovered. There is only one node actually that's remaining, but the robots don't know that. All they know is the graph up to distance 1, 2, 3 has been learned. They have yet to learn the graph up to distance 4 from the source node. So the way it works is the Explorer robot takes the token and places it on this empty node. Now, how do you do that? Well, because the robots have learned the graph up to distance r, they're aware of all the edges leading out of the graph. That is, up to distance r, they're aware of all the nodes as well as internal edges. And they know that, okay, from this node, this edge leads out, this node, this edge leads out. What they don't know is, from two separate nodes, do those edges lead to the same node or not? So this is what you try to learn. And the way it happens is as follows. Explorer and token move together. They go to one of these nodes. They go to one of these nodes that has an edge leading out, and the token is placed at this node, and subsequently Explorer goes back, and it goes and explores each of the other edges. Now, in this picture, there's only one edge, but there could be multiple other edges. And the point is to learn which edges lead to the same node. And once this is done for this node, if there were other nodes at this, if there were still edges that led out of this ball of radius r, the token explorer would explore those edges as well. In this manner, the token explorer will learn the graph up to distance r plus 1. And this is repeated until there are no more outgoing edges. Now, this previous technique, it assumed that both robots were non-Byzantine and took all of n cubed time. But that's not the world we're living in, right? If either one of those robots was Byzantine, the technique fails. Because what did we need? If this token, when it was placed here, if it decided to move away, when this explorer came here, it would see, oh, you know what? There's no token here. Maybe it's a different node. And then its internal view of the graph would be incorrect. So how do we deal with this? Well, we use a majority rule. And what does that mean? If there are a majority of good robots, that is, the number of bad robots is less than n by 2, then what we can do is we can have each robot pair up with a given robot pairs up with every other robot and constructs a map with each of them. And then it takes the majority of the maps And because there are more than n by 2 good guys, there will be more than n by 2 good maps. In other words, the same map. And so this majority map will be the correct map, and all good robots will learn it. The only catch is, in order for these robots to pair up with each other, it would take O of n such pairings. And remember, for a given pairing to construct the map, it takes n cubed time. So totally it would take n power 4 time. Now, how can we reduce this time? Well, if we could get a better guarantee on the fault tolerance. In other words, if our restriction was harsher, instead of saying, you know what, there could be up to n by 2 minus 1 bad guys, if we say, no, there'll be much less. They're only going to be up to n by 3 minus 1 bad robots. We can do something a little clever. So now, what you can do is, you can divide the robots into 3 groups, equisized groups. Let's call them Group A, Group B, and Group C. What you do is, you alternate the groups such that one of the groups will be an explorer, and the union of the remaining 2 groups will act as a token, such that the majority of robots will represent the explorer, the majority of robots will represent the token. Now, two of these pairings will succeed, because since there are less than n by 3 bad guys, you can really only do something bad if all of these bad guys end up as the explorer. But if these bad guys end up in one of the groups that forms a token, they can't have an impact. In other words, if you just construct the map 3 times, where A, B, and C, you alternate them, so then B, A, C, and C, A, B, 2 of them will produce a good map, 1 of them might produce a bad map. So in 3 pairings, you can find a good map. So totally O of n cubed rounds are used. Now, what did we do? We constructed the map. Now all the good robots have learned what the whole graph looks like. In fact, they have the same idea what the graph looks like. But that's not enough, because we still need the robots to settle. You'd say, okay, yeah, this is pretty simple, right? Because recall from Anisar's part of the tutorial, what do we normally do? We just use a DFS style algorithm. Have, let's say, the lowest ID robot settle down, and the rest of them perform a DFS. So in this situation, if all robots started here, 1 is the lowest ID robot, so it will settle down, and the remaining will explore. When you get to an empty node, 2 is the smallest robot, settles down, these guys come back, repeat it, so on and so forth. Everything is great, right? No. Everything is great when everybody was good. But the moment even one of them is bad, you can run into problems. Why? Because specifically, we want the lowest ID robot to settle down. So let's look at this again. Suppose 1, the lowest ID robot, is in fact Byzantine. What it can say is, what can happen is, it can tell everybody else, hey, listen guys, I'm gonna settle down. And they're like, okay, sounds good. So they move on. But because 1 is Byzantine, it actually didn't settle down, it also moves on. And now everybody here talks to each other, and the lowest ID guy is supposed to settle down. Who is the lowest ID guy? Byzantine guy. So it repeats the same thing it said before. It says, I'm going to settle down, but it doesn't. In this way, the robots never settle. This is bad. So what we do is, we have to address the following issue. Byzantine robots can lie. So we need to remember those robots who have lied and remember that they're bad guys. How do we do this? Well, each robot will remember a blacklist of known Byzantine robots. And basically, for a given robot R, all the other guys are considered good guys until they act badly. And what does it mean to act badly? Well, you just saw it. For example, robot 1, it said it would settle down somewhere, but then it showed up somewhere else. When robot R sees another robot, say 1, act like this, it adds 1 to its blacklist. Now, that's fine, but still, how do you actually settle down at a node once you have this blacklist? So let's actually look at that. Let's look at, for a moment, let's assume that we end up at a node such that we have a node where there are 3 robots, R1, R2, and R3. Importantly, R1 is Byzantine, whereas R2 and R3 are good guys. And the Byzantine guy, we don't really care what its blacklist is, so let's just pretend it's empty. For the good guys, R2's blacklist is empty. That is, it doesn't know R1 is a bad guy. But for some reason, R3 knows R1 is a bad guy, so it's remembered this. Now, the way we have them settle down is interesting. Recall that when I talked about randomness earlier, I talked about this leader election and utilizing sub-rounds because, well, communication is free. We again make use of this notion of sub-rounds and that communication is free. What we do is we divide a given round into n sub-rounds, and we have everybody raise their hand and say, hey, I want to settle. And in sub-round I, basically these robots take up an ordering according to the IDs. So let's say R1 has the smallest ID, so it's, let's say, rank 1, R2 second largest, so rank 2, R3 is the largest, so it's rank 3. Now, in sub-round I, the rank I robot decides whether it'll settle or not. And how does it decide whether it'll settle? Well, it looks at everybody who's already claimed to settle and sees if one of those guys is a non-Byzantine guy in its view. If so, then this guy doesn't settle. If everybody who's claimed to settle is a Byzantine guy, or in other words, no one else has claimed to settle, then this guy will settle down. So more concretely, initially, everybody, all these 3 robots, one will settle down. In sub-round 1, R1 says, fine. And of course, these guys don't make a decision. In sub-round 2, robot 2 looks at the previous people who settled down. So for only R1 settled, it looks at its blacklist. Is R1 there? No. So in R2's mind, oh, it looks like a good guy settled down. So R2 won't settle down. Now in sub-round 3, R3 looks at the previous people. Its blacklist has R1, so it doesn't care what R1 said. When it looks at R2, R2 said, hey, I didn't settle down. So R3 looks at the current setup and says, you know what? There are no good guys who have chosen to settle down. I'll settle down. And so it chooses to settle. If this process is repeated, then we show that in O of n rounds, all the robots will settle down using this DFS on the spanning tree of the graph. And we know what the spanning tree is because, recall, we already constructed a map of the graph. So in this way, all the robots can settle down. Now, when it comes to open problems in future work, one open problem is to reduce the time to solve this problem. It's probably not clearly shown here. One of the major roadblocks here is the time to gather. So what I showed you is, assuming the robots were already gathered, it only took n power 4 time or n cubed time, depending on the fault tolerance. The moment you introduce gathering into it, the time skyrockets to something like n power 9 or tilde of n power 9 time, which is astronomical. So if you're interested in this, that's one avenue to attack. And of course, the other thing is, for the given tolerances we set, or even for maybe if you assume a higher tolerance, can you do things faster? Or sorry, a lower tolerance, can you do things faster? Now, with that done, we'll talk about global communication. But just to preface this, I won't be describing, I won't be doing a deep dive for global communication because I'll be pairing it with the dynamism and I'll do a deep dive there. You'll see why once I get to it, but let's first explain global communication. So first of all, what is it? Well, robots can communicate with each other in every round. Previously, robots that were co-located could communicate. But if they were not co-located, in other words, if they were not occupying the same node in the same round, they couldn't communicate. Global communication is not this. Global communication is like, it doesn't matter where you are, I can talk to you. And things, why would you care? Well, the things, this is, global communication is a property, I mean, it's a setting that has been studied for other problems. And it's interesting to see what effect global communication can have, because it usually allows for faster algorithms or less memory. Now, what's been done before? Well, they study the time, again, they studied the memory time trade-offs when global communication is allowed. And they were able to develop better algorithms with better trade-offs than if you only used local communication. Another line of work was dispersion of mobile robots on grids. Basically, in this paper, there is also a global algorithm, and same thing. It gives good trade-offs because we allow global communication. Now, coming to why I didn't want to deep dive here, but I want to postpone it to dynamic graph setting. Thing is, global communication is also used in tandem with some other powers to actually solve dispersion in a dynamic graph. So I would rather just illustrate this being used there. And with that, we come to the final extension that we'll talk about in this part of the tutorial, dynamism in graphs. So first of all, what is it? When we look at dynamisms, or rather I should say, so far, the dynamism that has been looked at has been when the nodes remain the same throughout rounds. It's only the connections between those nodes that change. In fact, this is something I can tell you right now that would be an interesting open problem, though you would have to be careful about how you define the problem. Essentially, what if you allowed node churn? What could you do then? That has not been explored, but it's also not been explored because the problem definition would have to change. Because if you allowed node churn, you'd have to be very careful about what happened to robots on those nodes. Since we didn't want, the initial papers didn't want to deal with that, they only were focused on edge churn. Because in any given round, the robots are always located on the nodes, so you'll never lose them when the edges change. And of course, why would you even study this? Because, well, like fault tolerance, the real world, there's less stability. Everything is more dynamic in nature. Faultiness, dynamism, constant change. Change is the only constant in our world. So when we come to what's been done, so Agarwal, Augustine, myself, Shankar K, and Sridhar, we looked at dispersion, deterministic dispersion in dynamic rings. We looked specifically at one interval connectivity and something we call vertex permutation dynamism. But the model was a bit different because up to now, most of these robots talk to one another. In this particular paper, we switched it up and we just had robots take a global view of the ring, and they were not allowed to talk to each other. But another paper that's more in line with the models we've been talking about is this paper by Kesham Kalyani, Mola, and Sharma in ICDCS 2020. Basically, they combine global communication with an extra power, which I'll get to in a second, in order to solve dispersion on graphs that experience one interval connectivity. And they do this even in the presence of crash faults. Now, what is the power they make use of? They make use of something called one-hop visibility. Essentially, when you consider a graph, let's take, for instance, this graph. If let's take robot number 2. So the nodes are the circles, and these numbers represent robots. So 6 is a robot with ID 6, 2 is a robot with ID 2, 10 is a robot with ID 10. When you consider the setting, one hop visibility means the following. This robot 2 can look at all nodes distance 1 away from it and see what robots are on those nodes. And one interval connectivity, this type of dynamism that we're getting to, essentially nodes stay the same, but the connections can change, but there's a restriction. The edge connections can change between rounds, but the graph must always remain connected. In other words, this is fine, this is fine, this is fine. We have no control over what the graph might look like, but it should be connected. That's all. Now, before we get to this big idea, I want to say one nice thing about this paper. You might ask, if you're trying to solve this problem in dynamic graphs, why do you need to bring up these extra powers? Why do you need to bring up global communication? Why do you need to bring up one-hop visibility? Well, the reason you need to bring it up is this paper shows that when in the absence of either one of those two powers, it's impossible to solve dispersion in one interval connected graphs. You need both powers in order to solve this problem. And how did they solve the problem? Well, what they do is they look for paths of multiple robot, basically from multiple robot nodes to empty nodes. So for instance, here is a node with multiple robots. Here's an empty node. Let's look at one path that leads to it. So here and here. Here's a robot with multiple nodes. Here's an empty node. Here's a robot with one node. And here's an empty thing. This is another path to an empty node. From a node with multiple robots through robots with only one, a path from a node with multiple robots to a node with no robots, such that the intermediary nodes all have at least one robot in them. Actually, exactly one. And the idea is you can actually figure out these unique paths because you have one-hop visibility and you have the power to communicate with people anywhere in the graph. So these guys can all communicate. That's why both powers are needed. Once you find these paths, just have the robots slide one over. So in other words, 10 goes down, 6 goes across, 5 goes here, 22 goes here, and you settle down. And in this way, you can slowly fill up these so-called holes in the graph, these empty nodes. Because there must always exist, if there is an empty node, if you assume there are n robots, then there must always exist a path from a robot with multiple nodes to this empty node. And why is that? Because the graph is always connected. So in every round, you can at least fill up one such hole. So eventually after O of n rounds, all holes are definitely filled up. Now, what are some open problems and some future work that we could consider? Well, this was done in synchronous setting. So can you extend it to maybe semi-synchronous setting or the asynchronous setting? Although even defining dynamism in the asynchronous setting would be non-trivial. So it's actually quite interesting. Secondly, can you handle Byzantine faults? Because the previous paper would handle crash faults, but what about Byzantine faults? Secondly, can you handle some different type of dynamism in the graphs? For example, T-interval dynamism. And can you have other types of dynamism as well? Now, with this, I conclude my talk, but I do want to just mention that, as Anissa also mentioned earlier, there are constantly new works actually coming out on dispersion. For instance, something I didn't talk about or mention here is this paper that came out in Sirocco, where they actually extended this problem dispersion to directed graphs, and they talked about what's possible and what's not. So there's always new stuff coming out. In fact, Someone over there might be able to extend it in some non-trivial, interesting way. And we'd welcome it and be very happy for it. So with all that said, I'd just like to ask if there are any questions. Yeah.
Questions?
I guess I have one question for now. I wanted to check the work with Byzantine robots. Do any of them consider strong Byzantine, or are they all for weak Byzantine?
I missed the one word you said. Are they all what Byzantine?
Weak. Do any of them feel strong Byzantine?
Okay. I heard it now. So in the paper, in the IPDPS paper, we have results for both strong and weak Byzantine robots.
So could you summarize somewhat quickly how to deal with the strong case?
Sure. If I recall correctly, there are two results for strong Byzantine robots. The first result is, like I said before, gathering is something that takes a lot of time. So the first result is when robots start in arbitrary initial configuration, you can solve this problem in exponential time, simply because the gathering algorithm takes exponential time. More interesting result would be if the robots were in a gathered position initially. If I remember correctly, it was that if there are at most n/3 robots, then you can actually solve dispersion from this gathered position, even in the presence of strong Byzantine robots, in n³ time, I believe. Although, don't hold me to that. I have to check the paper to double check to be sure.
Okay, there at least somewhat recently, there is a polynomial time gathering of strong under strong Byzantine assumptions. The number.
Which paper? Do you know the paper?
Off the top of my head, one of the authors is Bouchard, so you could search Bouchard.
Okay, yeah, sounds good.
But you need square root, the number of faulty robots, square roots of the number of robots. So the number of good robots needs to be quadratic in the number of Byzantine robots, but you can do it in polynomial time.
Okay. Wait. Square root. I'm aware of a square root result, but that was for weak robots. This is for strong robots?
Strong, yeah.
Oh, this is so cool. Oh, this is really cool. Okay, thanks for telling me. This is neat. Okay.
Questions?
Any other questions?
No. I think that's it with the questions.
Okay, well, I just want to say thank you everybody for coming. Well, okay, I'm sure Anissa might want to say something as well, but thank you all for coming. Of course, if you want to ask questions or anything, feel free to email me. I always love to talk about robots, especially this problem, or any other problem, but I'm always available. Feel free to email me or anything. Thanks. I guess, Anissa, if you have any closing words. Okay. All right, then. Well, I guess that's it for this tutorial. Thank you all for attending. Thank you, Shreyas, for handling things on that end. We really appreciate it. Have a great day, everyone. Take care.